All right. Hey, everybody. Welcome to my home classroom. So, we're going to start off by talking about volumes today. So, we've been talking about area between curves, but we're not going to stop there. I think I told you guys a little bit about this last week. We're going to talk about what happens when you rotate curves around axes. We're going to start pretty basic today. I'm going to go through some examples with you. I'll give you guys some practice to try on your own, and I was really happy to see a lot of you responded to Google Classroom today. If you haven't yet, just please make sure that you get on board in the next couple days, because this is going to be really important for you guys to keep up with. So, on your notes, which I posted to Google Classroom, I'm just going to kind of talk through the basics, and then I'll go through some examples. So, what happens if I give you some curve? It doesn't matter what the curve is. It could be basically anything. We'll talk about different functions in a little bit. So, what if the curve looked like this? We want to talk about the x value from A to the x value to B. So if I were to take this curve and basically rotate it around the x-axis, so take it and literally turn it so it becomes a 3D shape. Well, what happens? It ends up looking something like this. So we're going to talk about how to find the volume of this solid that's created when the function is actually revolved around the x-axis. So basically what happens is we can kind of take a cross section or almost like a little chunk of that solid that's formed, and we can kind of turn it into like a shape that we're more familiar with. So hopefully by this time in your math career, you're familiar with the cylinder, which is basically what ends up happening when you take a little chunk of that solid out and you kind of turn it into something a little bit more simple. So we're going to talk about the pieces of the cylinder to kind of help us get the actual formula per se to find the volume. And then, like I said, we'll get into some examples. So basically what happens is when we end up taking this cross section out, there's a little chunk of this solid that ends up coming out that's actually got a height of a particular, I guess I should say expression. We've talked about this before. We've talked about it when we were doing area between curves. We talked about it when we were doing in the last section. This actually ends up being something called delta x, or the change in x. And if you kind of were to turn that cylinder on its side, it actually ends up being the height of the cylinder. And something special actually happens with the face of it. I know my drawing is really, really bad, so I mean, you guys are gonna have to bear with me a little bit. But this face of this cross-section ends up being a circle. So we know the area of a circle is pi r squared. But this is a little bit different because the radius of this cross-section changes based on where we are in the actual solid. The radius here is a little bit smaller. What happens if I were to take a cross-section over here? The radius is a lot bigger. So what ends up happening is the radius is actually the height of the curve. The radius here, the radius here, the radius here, the radius here is actually just the height of that curve. So the radius actually ends up being our function, f of x, because that's what it is. Our function is the actual height or the radius of that cross section, no matter where we are in that shape. So what we can say, and I'll erase this so that I have a little bit more room. A little bit ridiculous. I need to find a bigger eraser than this, but I'm making do with what I have. So what we can say is the volume of any shape, no matter what the curve, the starting curve is the general formula volume is going to be equal to pi, which we said was kind of part of our face of our cylinder down here, times the integral from A to B, which is whatever the x values are that we're working on, of our function or our radius squared times delta x, because remember that the volume of a cylinder is pi r squared h. Well, there's the pi, there's the r squared, there's the h, the delta x. So as we work through our examples, we'll kind of see this over and over again. I'll kind of walk you guys through how to actually plug that into your calculator. This is where I always say any questions, but since you guys aren't here, I can't. This is weird talking to a phone, but like I said, we'll kind of get through this together. let's look at example 1. And you guys have this on the notes that I posted on Classroom. I'm going to do my best. You know what? I'm going to do this with this little eraser. It's a little ridiculous. I'm going to do my best to draw pictures and kind of walk you guys through this. Like I said, I kind of have limited resources here at my house, but we're going to do with what we have. So our example 1 is asking us to find the volume of the solid obtained by rotating the curve y is equal to x squared about the x-axis. And we're talking about the x values from 0 to 1. All right, so I'm going to do kind of a rough sketch on what you guys have on your paper already. So here's my function x squared. Here is my curve from the x value of 0 to the x value of 1. And basically, I want to take this portion of my curve and I want to rotate it about the x-axis. So what ends up happening is we end up getting kind of like almost like a cone shape. If I were to kind of take this and kind of replicate that down below and actually turn this into like a solid here. So if you kind of think about that in 3D, like that's what your shape would look like if you were to rotate it about the x-axis. And like we did on the other one, I'm going to kind of take a cross section here. The cross section is still going to be circular. It doesn't really matter in terms of what type of function we're working with. It could be something squared, it could be linear. We'll talk about a square root function. The cross section ends up looking the same. So the cross section is this little cylinder here. So my volume, what we were talking about before with the volume ends up being pi times the integral. We're talking about the x value from 0 to the x value of 1. So those are my limits, 0 to 1, of my function squared. So my function is y is equal to x squared. So here's my x squared. And since I'm talking about the radius squared, remember the cylinder volume formula is pi r squared h, so I'm going to square that, times the height of dx. So I end up with volume is equal to pi times the integral from 0 to 1 of x squared squared dx. I'm just going to simplify this a little bit. And what I'm going to have you guys do is I'm going to have you use whatever the virtual calculator is that you kind of explored today to actually do this integral. So I'm going to rewrite this as the integral from 0 to 1 of, I'm going to put pi times x to the 4th dx. And this is basically what I'm going to put into my calculator. So I've got my 83 plus here, my ancient 83 plus when I was in high school. Turn on my integral, so pi times x to the 4th, put in my 0 to 1, hit enter. So my volume, I don't know how far down this you can go that you can actually see this, is about 0.6283. So that would be the volume of this function, x squared, revolved about the x-axis from the x value of 0 to the x value of 1. So whatever the calculators that you guys chose to use, please just make sure that you're getting this answer. And if you are not, please ask me for help on either like the Desmos or the Wolfram Alpha or the Calculator X app, and I can try to help you kind of get that right answer. I think a lot of you did a good job today posting that thing on Classroom so that I was able to see that most of you knew how to work at least one of those 3 options. All right, let's talk about a different function. So there is my quadratic type function. Let's move to a square root function. So now we want to find the volume of the solid obtained by rotating the curve of y is equal to the square root of x. And we want to rotate that about the x-axis. And we're talking about the x values from x is equal to 0 to x is equal to 4. So I'm going to draw myself a nice little diagram here. Make it a little bit smaller than the last one. So 1, 2, 3, 4. I'm going to try to get as accurate a curve as I can. So I know I'm going to start at 0, 0. Square root of 1 is 1. So that'll be 0.11. And then I'll just do x value of 4. So square root of 4 is going to give me a 2. So this is going to be what my curve is going to look like. So my square root of x from 0 to 4. And then I want to rotate that about the x-axis. So I'm going to draw myself my kind of like reflected piece there. This is going to be what my solid would look like if I were to revolve that about the x-axis. Again, my cross section here does end up being circular, kind of cylindrical in nature. And when I set up my integral, volume is going to be equal to pi times the integral from my x value of 0 to the x value of 4. And I'm going to put in my square root of x. Remember that I'm going to square it because that's the pi r squared h, and my h is my dx. So I'm going to simplify this a little bit, same way I did the last problem. So pi times the integral from 0 to 4. The square root of x squared actually just gives me x dx. So the way that I'm going to plug that into the calculator, I'll move that pi back into the integral. So that's going to be the integral from 0 to 4. So it's going to be pi x dx. And again, using whatever the calculator is that you feel more comfortable with. I'm going to type this in, pi x from 0 to 4. And you should get approximately, like, how much you guys can see here, 25.1327. So that would be the area of this y is equal to the square root of x revolved about the x-axis from the x value 0 to x value 4. The volume would be approximately 25.1327. And again, make sure that you're typing that in and confirming that the online calculator that you're using is going to be working for you. All right, we will do one more function. So we've done a quadratic, we've done a square root. Let's talk about a linear function. This one's going to be worded a little bit differently. So now we're looking for the volume of the solid obtained by rotating the curve x plus 2y is equal to 2 about the x-axis. And this time it's giving us kind of like not x values, but an x value and a y value. So it's asking us to go from x is equal to 0 to y is equal to 0. So let's talk about this one. So I'll rewrite this up here. X plus 2y equal to 2. And we're going about the x-axis. And we're going from x is equal to 0 to y is equal to 0. So I'm going to do a little quick sketch of what this is going to look like. But before I do that, I'm going to get this into slope-intercept form so that I know like exactly what my y-intercept and my slope is. So I'll move my x to the other side. So 2y is equal to negative x plus 2. Divide everything by 2. Y would be equal to negative 1/2 x plus 1. So draw myself a quick little coordinate plane here. I'm going to just actually number my axes a little bit spread out here. All right, so my intercept is going to be 1, and I'm going to count a slope of negative 1 over 2, negative 1 over 2. All right, so my line, I'm just making sure that I'm graphing that correctly. I think that's right? Nope. That's because I spread that out a little bit. Okay. Negative 1 over 2. Yep. There you go. Can you tell we haven't been in school for a little bit? Not like this is unusual, though, because I make mistakes when I'm doing work on the board anyway. All right. So this is going to be the region that I want to revolve around the x-axis, because this is going to basically tell me that my x value is 0 over here, but when y is 0, my x value is going to be 2 here. So I'm really going to be using in my integral x is equal to 0 to x is equal to 2, because that's where the y value is 0 over here. All right, so when I actually replicate that, or kind of like, revolve that around my x-axis, I'm going to end up getting something that's going to look something like this. So if I kind of imagine that triangular region as kind of being that like solid almost, or that 3D solid, this is going to be what my region's going to look like. It's going to be almost like a cone shape, but this time it's like facing the other way. Doesn't matter which way your shape is facing. So when I go to grab a cross section there, again, it's still going to be circular or cylindrical in shape when we kind of like extract that from the actual region, but my volume formula is still going to end up being a little bit like the other ones. Our setup's just going to be a little bit different. So it's going to look like pi times the integral of the x value of 0 to the x value of 2, because again, that's where my y value is 0. And then I'm going to take this whole thing, since I'm integrating with respect to x, this is going to be my radius. So I'm going to take that quantity, negative 1/2 x plus 1, I'm going to square that, and then I'm going to multiply it by my height, or my dx. So just be careful about when you're plugging this into whatever that calculator is. Like I said, I think I told you guys I have like an old version, and you have to like plug it in really carefully, and then it like won't calculate it correctly if you like mess one thing up. So when I go to move that pi into the integral, just make sure that that negative 1/2 x plus 1 quantity squared stays in a set of parentheses. So I've already done this work, so I don't have to like waste time actually plugging into my calculator. I got approximately for my volume about 2.0944. And that would be the volume of this region, again, rotated about the x-axis from the x value of 0 to y value of 0. But again, where that y value is 0, my x value is 2. So thanks for watching. If you guys have any questions, please do not hesitate to ask me. I'm going to give you guys some practice problems, probably like 2 or 3, so that you can practice this on your own. All right. Have a good day.